Alright guys, today what we're going to look at is position, velocity, and acceleration versus time graphs under two different examples. One that we've been dealing with quite a bit, constant velocity. That's when you're moving a certain amount of space in a distance in a certain amount of time. And then we're going to be talking about constant acceleration, is what we've been working into lately. That's a good example of that is dropping something in free fall or gravity. We've hit this several times, so this is kind of a review. But guys, if we have a constant velocity example, we're going to get a position versus time graph that's linear, and it's going to go something like that. Okay? And in this case, guys, if we go 125 meters in 5 seconds, we could come up with our average velocity, and we can find average velocity by taking change in position over change in time, which in this case is 125 meters over 5 seconds, which turns out to be 25 meters per second. Now, if we have a constant velocity, which is shown by the linear nature of that curve, then we know that the slope of that curve gives us our instantaneous velocity. And so at any particular point, if we find the slope, then we'll have our instantaneous velocity, and because we're constant, the instantaneous and the average is the same. So our velocity versus time graph would be a horizontal line coming in there at 25 meters per second. Now, if we're going at a constant velocity, that should probably register in your brain that we're not accelerating at all, because we're keeping a constant velocity. So the slope of this curve, this velocity versus time curve, is going to give us our instantaneous acceleration, and the slope of that curve at any particular point is 0. So our acceleration versus time is going to come in here and be right at 0. Really, really simple example of constant velocity and what it would look like in a graphical form. Now, if we were to draw this line going downward, which means we would be traveling in the opposite or negative direction, our slope then would be negative, which would move this line down into the negative, and it would go across here at negative 25. But because we're going at a constant velocity, this is linear, which means a constant velocity, our acceleration would once again remain 0. Okay? So that is a good example of a constant velocity type problem. Now we're going to move over to our constant acceleration example. And guys, keep on remembering the slope of the position versus time yields instantaneous velocity, which we did back here. And the slope of the velocity versus time yields your instantaneous acceleration. So in this case, guys, if we're accelerating, our velocity is going, and we're accelerating at a constant rate, our velocity this time is going to be linear and increasing up like that. And when we would do that, guys, every second, what that means is we're covering more distance every second that we go across. And so we've reviewed this enough times to know that this is going to be a quadratic type curve or a parabola. And guys, if we look at that, it makes sense, because if I take the slope at this particular point, it's going to be the tangent line. And that slope is not very high, so that would yield us a pretty low instantaneous velocity. As we move up the curve, and I actually kind of drew that incorrectly, that should keep curving up like that. That slope here, the tangent, gets higher. And if we were to move up here, it's getting even higher. And so as we take that instantaneous slope or velocity, we get subsequently higher velocities. Okay? And keeping in mind that the slope of this curve yields us the velocity, and the slope of the velocity versus time yields us the acceleration. So if we take the slope at any particular point here, we're going to get the instantaneous acceleration. And because that's linear, we know we have a constant slope. And if we were to be dropping an object on the Earth, it would be accelerating at a rate of about 9.8 meters per second squared. So this example, I've made that, and we would get an acceleration that remains constant and stays at about 9.8. We're going to get into kinematic equations here in a bit, and we'll be able to figure out that, well, it's pretty obvious. If you're accelerating at 9.8 meters per second in 5 seconds, you would be going 9.8 times 5, or right around 50 meters per second. and we would have covered a distance of about 125 meters, which we will verify when we get into using the kinetic equations. All right, so just to review and hit it one more time, the slope of the position versus time yields us the velocity versus time, and then the slope of the velocity versus time yields us the acceleration versus time. One last piece, if you're a calculus student, you've already taken that, the slope of this curve we obtain by taking the derivative, and so the derivative of the position versus time yields us the velocity, and the second derivative of the position versus time yields us the acceleration. If you haven't had calculus yet, don't worry about that. That's just a tie-in to calculus so that students that have taken it can feel like they got something done there. All right, that's position versus time, velocity versus time, and acceleration versus time.